Last time we introduced the concept of the electric field. We began this pre-lecture by building a geometric representation of the electric field produced by a point charge. The field produced by a point charge is spherically symmetric. Its direction is radial from the point charge. Therefore, we'll start by drawing radial straight lines emanating from the point charge distributed in a spherically symmetric way. These lines provide an unambiguous representation of the direction of the field at any point in space. The amazing thing is these lines also provide information about the magnitude of the field at any point in space. Consider a sphere of radius r centered on the point charge. We see that the lines we have drawn are distributed uniformly over the surface of that sphere. As we increase the radius of the sphere, the number of lines passing through the surface stays fixed, but the surface area increases as r squared. Therefore, the density of these lines passing through the surface decreases as 1 over r squared, exactly the same decrease that the magnitude of the electric field experiences. Consequently, we can represent the magnitude of the field at any point P as being proportional to the density of lines passing through the surface of the sphere that contains point P. If we make the number of lines drawn proportional to the electric charge, these lines provide a complete picture of the electric field at every location in space. For example, if we increase the magnitude of the charge by a factor of 2, we'll have twice as many lines emanating from the charge. The density of these lines at any fixed distance from the charge will therefore also double, indicating that the electric field at that distance has also doubled. We call these lines the electric field lines, and we will use them to represent the electric field produced by arbitrary charge distributions. It is common to rewrite Coulomb's law in a way that reinforces this geometric interpretation by introducing a new constant, epsilon naught, as shown. I.e., if we choose n, the total number of field lines produced by a point charge q, to be equal to q over epsilon naught, then we see that the magnitude of the electric field at any point on the surface of a sphere of radius r centered on the charge will just be equal to n over a, where a is the surface area of the sphere, which is 4 pi r squared. This geometric representation we have just built will prove to be very powerful. The number of field lines represents the magnitude of the charge that produces an electric field throughout space, whose direction is given by the direction of these lines and whose magnitude is proportional to the density of the lines.